Good day, everyone, and welcome to Organic Chemistry 1 or FAR 2000. This is Lecture 1, and of course, my name is April Johnson. So, today I'm going to give a brief introduction to organic chemistry, and then I'm going to do a review of drawing and naming compounds. I'm also going to review chemical bonds and such as covalent or ionic bonds. And then I'm going to finish off with types of reaction, so like elimination, addition, etc. So, as I said today, the title of today's lecture, Chemical Bonding. So, in this introduction, I'm introducing organic chemistry. So, the first organic synthesis was the accidental discovery in 1828 by Frederick Wöhler, and that is his image. He discovered that urea, which is organic, could be made by evaporating an aqueous solution of ammonium cyanate, and that is the reaction. So prior to that, it was not thought that we could make in a lab what was made by nature or made by God. But now we know better. So next I'm going to go into the chemistry of carbon. So as we know, organic chemistry is the chemistry of carbon compounds. And as we also know, most of life's processes are supported by the chemical reactions of complex organic compounds, such as these enzymes. So we know that enzymes are complex organic compounds, as we see in the image here. Well, we're not seeing the carbon, but we know that these are organic compounds. And then next on our list is the hormones, right? So we're familiar from biology with a variety of hormones seen here, or histamine, gastrin, etc., etc., and all of these are organic compounds. Proteins as well. We are familiar with actin and myosin, insulin. All of these proteins are organic compounds. And next are carbohydrates. So previously that was more biology. Now we're getting into our chemistry, where we're seeing actual molecules and structures here. So for example, cellulose, starch, glycogen, etc., we can see clearly here that these are organic compounds. And then also our lipids or fatty acid. So these are long chained. This is a saturated fatty acid with a carboxylic acid at the end here. And then we have a variety of lipids. So clearly, again, another organic compound found in nature. And then RNA, DNA, right? The backbone of which nucleic acids, again, organic compounds. So as we can see here, from the variety of life processes depend on organic compounds and organic reactions. So that is why we are studying this group of compounds. So that leads us to our first question, which says the structure shown above represents A, lipid, B, carbohydrate, C, nucleic acid, or none of the above. So, so if you answer D, which is none of the above, you are indeed correct. That leads us now to our follow-up question 1. And of course, I expect that you will have this answer at your next class. So all follow-up questions should be answered prior to or at least attempted by the next class. So this question is, what is the name of the compound seen in the structure above? All right, so the next thing that we're going to look at is line angle diagrams, and it is the language of advanced organic chemistry. And clearly, you are all advanced organic chemists, seeing that you're doing a level 2 chemistry course. Okay, so we see here that we have the condensed version of the structures here in blue, and then we have the line angle diagrams above them, right? So as we can see, we cannot see the hydrogens here, and they're at an angle, as you can see for all three compounds. So you must be comfortable doing an advanced organic chemistry course in drawing and understanding these line angle diagrams. So I'm going to play a video now for further explanation. So on screen we have the same compound, methyl butane, and of course it's methyl butane because we have 1, 2, 3, 4 carbons, and we have methyl here at position 2. Alright, so we have the same compound but just drawn differently. So the structure in green seen here represents the condensed version of the structure, and then of course we have the line version in red. Alright, so I want to make it very clear how we convert from a condensed version to a line version seen in red. Alright, so I'm going to redraw my methyl butane here. Alright, so we have our 1, 2, 3, 4 carbons, and we have the methyl at position 2. Alright, so what we must appreciate that at every junction there is a carbon, right? So at the end, and perhaps I should use a different color for that. At the end, we have a carbon here, we have a carbon here. At the junction here, we have a carbon, we have a carbon here, and we have a carbon here. So in total, we have 5 carbons, all right? So that's the first thing that we must appreciate, that at every junction, there is a carbon. All right, so the next thing that we must appreciate is that there are hydrogens present that we are not seeing in the line version. All right, so let me pick a different color. All right, so let's go with green. All right, so for every junction, so firstly we're looking at this junction first, right? We have to identify how many carbon atoms are attached to it. Okay, so we can say without a doubt that we have 1, 2, 3 carbons attached to it. Every carbon, as we know, has 4 bonds. Okay, so if 3 bonds represents bonds to other carbons, then the 4th bond must be a hydrogen. Right? So if we have 3 bonds to a carbon, the 4th one must be a hydrogen, as seen down here. Right? And so let's look at one of the end carbons, right, which we refer to as methyl. So if we look at, the end carbon, we look, okay, how many, and let's get rid of our numbering here, right? So we say how many carbons are attached. So let's work with this one. How many carbons are attached to it? If you answered 1, then you are correct. So if we have 1 carbon that's attached to it, how many hydrogens are present? Okay, So let's redraw our compound here, right? So if we have one carbon attached to it, then obviously we must have 3 remaining carbons, right? So that represents the end one. All right, so let's look at another carbon. Let's look at this one, right? And my question is, how many carbon atoms are attached to that carbon atom there? If you answered 2, then you are correct. If we have 2 carbons that are attached to that carbon, how many hydrogens therefore are attached to it? Well, if you guess 2, then you are learning. All right. So that's how we go from a condensed or an expanded structure to a line and vice versa. All right. So we must, in summary, understand that at every junction there is a carbon, and then we have to account for 4 bonds with a neutral carbon atom at all times. All right, great. So the next thing that we're going to look at is functional groups, right? So from high school we have been introduced to functional groups. So we know about our carboxylic acids, for example. We know about our amides, and this list looks very long, but it actually really isn't. Again, for the primary, secondary, and tertiary amine or amide here, we have, for the primary, there are 2 hydrogens attached to the nitrogen, and 1 for the secondary, and no hydrogen for the tertiary amide. We know about our nitrile, we know about our aldehydes, we know about our ketones, we know about our alcohols, and of course the alcohols can be subdivided into primary, secondary, and tertiary again. And similarly, for the primary alcohol, there are 2 hydrogens attached. For the secondary we have 1, and for the tertiary we don't have any hydrogen attached to that central carbon. Or phenol, which we know is a benzene ring with one of the hydrogen being substituted for a hydroxyl. We know about our amines, which are broken down again into primary, secondary, and tertiary in a similar fashion. We know about our ethers, and we can look here. We may not have met the sulfide or the thioether here, so this might be a new one. So that is a sulfur, as a sulfur that's bonded to 2 carbons, as opposed to the ether that we're familiar with, oxygen bonded to 2 carbons. So that's either sulfide or thioether. And of course we know about our alkenes, alkynes, alkanes, nitro, halides, etc. Alright, so this leads us to question number 2, which says identify all functional groups in morphine and amoxicillin. So take a minute and look at these structures, and you can also go back to the previous slide to assist with this. So if you answered this correctly, you would have had labeled this group here as a primary amine. We have some secondary and tertiary amides. We have our carboxylic acid. We have our thioether, which we just met a while ago, and our aromatic ring. And of course all of this represents our phenol. And for the morphine, that is for our amoxicillin. And for our morphine, we have a similar arrangement here. In this case we have a tertiary amine here, secondary alcohol or ether, and of course our alkene. We haven't mentioned them in either of them, but we also have our alkanes. So question 3 says, draw the structure of the following compounds. So go ahead and write the names out in your books and attempt this question. To assist with this, I'm going to play this video. Alright, so on this slide, I really just want to distinguish between propane, propyl, and isopropyl. And if we get this, we can get the others. Alright, so just to recap a little bit, our alkanes, which we remember from high school, that, once it's a base name, it ends with A-N-E. That is why we have propane as seen here. And if it's a substituent, then it's now an alkyl. So that's why we have propyl and isopropyl. All right. So again, we know for propane, isopropyl, and propyl, we have 3 carbons. Right. That is common. All right. So let's look at our substituents because we must already know and understand propane. Alright, so what we're looking at here is the point of attachment, right? So as we can see here, the point of attachment for propyl is at carbon 3 here. So this carbon is attached to something, okay? And here for the isopropyl, it's the middle carbon that is attached to something, alright? And so as seen in our 2 structures below, these are examples, right? And so we see our cycloalkane here, and the point of attachment is to carbon 3, right? And then for our second cycloalkane, the point of attachment is to our carbon 2. I hope that clears it up. All right. So just to note here that, please be familiar with the others. So it's not just propyl. So there are several variations of butyl as well. We have 1-butyl or otherwise called N-butyl. So the ones that are in brackets are other names for, these at the top. So we have 2-butyl or S-butyl, right? So again, it only differs where the point of attachment is. But just to note from the video that the numbers used in the video does not represent IUPAC numbering. It was used solely to explain the point of attachment. So here when we have 1, 2, 3, we're not saying this is carbon 3, we're just using it to explain the point of attachment. So there's no relation to the IUPAC name. And secondly, isopropyl is the same as 2-propyl, which is necessary information to answer one of the questions. All right, so if you drew A as menthol and B as ethchlorinol, then you are indeed correct and on your way. So I'm going to play this video which hopefully further explain why we drew one of these structures as we did. Alright, so I've already redrawn the structure, so I'm just going to break down the numbering and the substituents. Alright, so the first thing that we need to look at is the fact that the base name is pent, right? And the fact that it's Pent means that the longest chain has 5 carbons. So let's go ahead and number our carbons. So we can, well, let's start from here. 1, 2, 3, 4, and 5. Alright, so the structure satisfies the 5-carbon requirement. Alright, so the next thing that we want to look at is the numbering. So yes, we could have numbered the other way. So if we number the other way, it would have been 1, 2, 3, 4, and 5, right? Which would mean that the chlorine would be at position 5 versus 1. Alright, so we have 2 options for numbering. We have the longest chain. It could be numbered the blue way or the red way. Alright, so hence we've already figured out that part. And then from there we can look at the what is attached to the longest chain. Alright, so we see here that we have an ene as well as a chloro at position 1, right? So if we just draw, for example, let's say, we're doing it blindly. 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5 carbons. And we said, okay, at position 1, I have a double bond, which is why we have En. And then I also have a chloro at position 1. And then we say, okay, there's nothing at position, there's no substituent at position 2. At position 3, we have an ethyl. So let's number this 1, 2, 3, 4, 5. At position 3, we have an ethyl. And what else do we have at position 3? We also have an ol, right? So at this position here, we have an ethyl, and we also have an alcohol. So we can go ahead and put in our OH there. At position 4, right? At position 4, we have ine. So at position 4, we have our triple bond. And that's basically it. So one thing or 2 things that we need to remember is that for the double bond, notice that it covers 2 carbons, right? And this is getting a little bit messy, but it covers 2 carbons, and the number that is counted is the first one, right? And then also for the ine, it covers 2 carbons as well. So it is messy, but let me go ahead. It covers 2 carbons, but the first one is counted. So I think that is the most crucial information that we can get from this. All right, great. So just to point here that note also the 180-degree angle of the alkyne, right? So every time you draw an alkyne, that angle must be 180 degrees. So I hope that clears up everything. All right, so we have follow-up question number 2. So you're expected to draw that structure for question 1 and write the IUPAT name for that structure seen in the second question. Alright, so this leads us to the second part of the lecture, which is a review of chemical bonds. So the first one that we're going to look at is ionic bonding. And of course, we know that's related to a crystal lattice. And then we're going to look at covalent bonding, which of course we know that we have both polar and no polar, sorry, non-polar covalent compounds. And then we're going to also review resonance. So the first of the chemical bonds that we're looking at is ionic bonding. So as you know, it's an electrostatic or attractive force between oppositely charged particles, and we also know that most ionic compounds consist of an arrangement, so we have positive and negatively charged ions alternately in a 3D structure called a crystal lattice, and we know about sodium chloride. So the strong electrostatic forces give rise to high melting point solids. So in polar solvents, the ions are solvated and the solutions conduct electricity. So that covers ionic bonding. And of course, we are familiar with how, as we said before, positively and negatively charged ions arranged in a 3D crystal lattice. So we see that here. And of course, we know that when a compound forms an ionic bond, that in this case, sodium would have lost an electron and chlorine would have gained an electron. And that is why we have ionic bonding. So the next thing that we're going to look at is covalent bonding. So we know that in this case, it's the sharing of electrons between atoms of similar electronegativity, and that is due to the ability to attract an electron. So the structural units are molecules with no net charges, can be solid, liquid, or gas, and we have polar and nonpolar. So the nonpolar covalent compounds do not dissolve in water or polar solvents such as methane. And polar covalent compounds, however, are soluble in water or polar solvents, and it ionizes slightly in aqueous solutions, and of course it does not conduct electricity, for example ethanol and glucose. So we are familiar with several compounds that come under polar covalent bonds. You know, we have water, we have CCl4, ammonia, or that is carbon tetrachloride, seen there. So a covalent bond in which the electrons are not equally shared because of a difference in electronegativity. So as we see here with hydrogen and oxygen, so because the oxygen is slightly negative and hydrogen slightly positive, there the electrons are pulled closer to the oxygen, and therefore we have a polar covalent bond. So the next thing that we're going to look at is resonance theory. And I do expect that you would have been somewhat familiar with this topic. So for some molecules or ions, more than one equivalent Lewis structure can be drawn. So we're using the carbonate ion here as an example. So we have carbon here in the center, and we have oxygen here with a double bond, and then we have two single bonds, which we know would be negative charge here, negative charge here. So how resonance comes in is that what we're seeing here is that this double bond can also be here as is as seen in this structure, and then the double bond could also be here as seen in this structure. So the structures are interconvertible by changing only the position of the electrons. Alright, so if we even follow this arrow, we can show how each structure are linked to each other via resonance. So we can show here, if we follow the red arrows, that the pair of electrons would move from the oxygen to the bond, which will now form a double bond, and then one of these bonds would break, as is represented by the arrow starting on the line, and then the pair of electrons would now reside on the oxygen, and that leads us to our second resonance structure. So these compounds are not identical but equivalent, and all the carbon oxygen bonds are of equal length. All right, so here just a very nice way of explaining the resonance theory is that if we consider a unicorn and a dragon as species that don't exist, imaginary species, and if we combined both of them, we end up with a rhinoceros, which is an actual living animal. So in resonance theory, we're saying that this unicorn is a resonance contributor, and we're saying the dragon is a resonance contributor. However, what actually exists is the rhinoceros, or the resonance hybrid. So let's tie that to these structures that we have seen before. So we're saying that this is a unicorn, doesn't exist in real life, and we're saying that this is a dragon, doesn't exist in real life, but what actually exists is the rhinoceros, right? Because the electrons are actually delocalized. It's not localized. It's not only here. It moves from throughout these three bonds, right? So this is what actually happens. This is the resonance hybrid. So whenever a molecule or ion can be represented by two or more Lewis structures that differ only on the positions of electrons, none of the structures will be a realistic representation of the molecule or ion. The actual molecule or ion is better represented by a hybrid or average of these structures, which is what I was trying to say. So again, the resonance theory says the energy of the resonance hybrid is actually lower than the energy of the contributing structures, right? So again, let's look at the resonance hybrid and the contributing structures. So we say this is a resonance contributor, this is a contributor, and this is the hybrid. So according to the theory, or what has been observed, is that the energy of the resonance hybrid is lower than the energy of any of the contributing structures, and resonance stabilizes the molecule or ion. So the fact that the ion can delocalize, that stabilizes the molecule, and again, lower energy is associated with increased stability. So if the resonance structures are equivalent, then the resonance stabilization is large. And then also, the more stable a structure, the greater the contribution to the hybrid. So let's look at that. So we have these two resonance structure here. If we look at formaldehyde, so we're considering formaldehyde, and we have these two resonance structures. And so the point we're making here is that the charge separation decreases stability. So this particular structure would be a greater contributor than this, because the charge separation decreases stability. So when all atoms have a complete valence shell of electrons, these increase stability. So these are the things that contributes to the stability. So we're seeing that the formaldehyde in this form would have be a greater contributor to the resonance, and therefore, let's go back to that side, and therefore the more stable a structure, the greater the contribution to the hybrid. So this is more stable than this, and therefore this is a bigger contributor to the hybrid. All right, so you may be considering for a second, is resonance the same as equilibrium? Let's see, are they the same? Well, let's look at the differences. So for resonance, as we have been saying, in resonance, the structures only exist hypothetically. Again, if we recall the dragon and the unicorn, they only exist on paper. While for an equilibrium, it's between two or more species, the structures are moving from one form to another. So in other words, they don't only exist on paper. Another thing that we need to distinguish between resonance and equilibrium is the arrow, right? So if we see this arrow, which is a straight line and two arrows at the end of the same line, this is a resonance arrow. And in contrast, this is a equilibrium arrow. So we have two arrows, one going in the forward direction, one going back. Okay, so this is a equilibrium arrow. Again, for the resonance, the connectivities are the same as we have seen, only the position of the double bond, lone pairs, and formal charges differ, in contrast to the equilibrium where the atomic connectivities differ. So, just to look back at some structures here, right, this would be resonance because the connectivities are the same, and well, we're not really seeing this is still a CH2, so the connectivities are the same for both, and we have the right arrow, right? In this case, the connectivities differ because we have a OH here and we don't have a hydrogen here. This is a CH3, so the hydrogen here is now here, and so the atomic connectivities differ as opposed to resonance where the connectivities are the same. So resonance is indeed different from equilibrium. So that leads us to question 3. So please comment on the equation shown below. Is it looking good? Are there any issues? Do you have any issues with it? So if you said, yeah, something is definitely wrong with it, then you would have been correct. So the only thing that's wrong with it is the fact that we have the wrong arrow. So it is not an equilibrium, but these are actually resonance structures. So the arrow is the only thing that is wrong. The movements of electrons are indeed correct. And that leads us to our follow-up question 3, which says draw the resonance structures for the molecules below. So the hint for A is that 2 R's are required for conversion to the other resonance structure. And then the hint for B is that the other structure or the other resonance structure has 2 charges. So attempt that and let me know what you come up with. So that leads us now to bond strengths. So the stability of a molecule is a function of the strength of the covalent bonds holding the atoms together. So the bonds of the same order between different atoms show a wide range of bonding energies. So if we just take, let's just take carbon-carbon bonds, for example, and just look at just look at the energies for single versus double versus triple. We see for the single bond, the bond energy being 346, for the double 602, and the triple um 835 kilojoules per mole. So obvious differences there, and so we can therefore say that the triple bond is definitely greater than the double, which is definitely greater than the single bond, right? So again, the stability of a molecule is a function of the strength of the covalent bonds, and we can see here that the triple bond is much stronger than the single bond based on the bond energy. So just another revision slide about chemical reactions. So we know that for every reaction, and then obviously that's related to the strength of the bond, that for every reaction we have bond formation and bond breaking, or else it's not a reaction. If we look at it, there are two ways in which bonds can be broken and formed. And so heterogenically, of course, we know hetero means other and homo means same. So in this case, if we have a bond, then both of the electron um, comes from one, for if the bond is forming to form this bond here. And if it's a homogenetically formed reaction, then we have one electron from one and one electron from the other. And so we have a homogenetically formed bond. And then for bond breaking, we're using the same prefixes, hetero and homo. However, in this case, the bond is breaking, so it's heterolytic cleavage versus homolytic cleavage, sorry. And this bond is breaking. So in hetero, the pair of electron goes to one atom, and therefore that atom becomes negatively charged, as opposed to the other, which is positively charged. And then for the homolytic cleavage, we have one electron going to each atom, and therefore we end up with radicals. So just in case you were having difficulty earlier with following the arrows, you're in luck, because we're doing a little revision now on the arrow movement. So if we recall homolytic or homogenetic, as we just mentioned a while ago, we're going to show how that happens with regards to arrows. So the movement of one electron is denoted by a fishhook arrow. So it's just one side of the arrow, as we see here. So when a bond breaks, remember the line represents two electrons. So one electron goes to A, the other goes to B. We end up with two radicals. And of course, to make a bond, then the fishhook arrow has to start from both, and where they join suggests that, okay, we have a new bond being formed. And of course, there are several other variations to this, but the key point here is that the fishhook arrow represents the movement of one electron, and the principle of arrow movement is the same, in that where the arrow starts is where the electron is coming from, where the arrow ends is where the electron is going, and we must know that, and we must be very comfortable with that. In contrast, when we have heterolytic or heterogenetic, either cleavage, bond forming, or bond breaking, we have movement of an electron pair, and that is two electrons, and we have a different arrow. So we refer to that as a curved arrow, So it's not a half arrow this time, it's a full arrow, and it shows that two electrons are moving, and it shows the direction of the electron flow as we have been saying. So here, this is a double-headed arrow. So this means that this pair of electron is forming a new bond with this hydrogen. This bond is breaking because the arrow starts there, and the pair of electrons now reside on the chlorine to form the chloride ion. So we have a new bond formed between the oxygen and the hydrogen. So we have our hydronium ion and chloride ion here. And again, for the chloride ion, the negatively charged chloride ion, that's the source of the electron, that is the nucleophile. So the arrow starts here, it ends on the hydrogen, and then this bond breaks, as is represented by the arrow starting on the line and ending on the oxygen. All right, so we end up with HCl and water. So just to reinforce that arrows move from a region of high electron density to a region of lower electron density. And we also must recall these very key terms which I have been using. So just in case you have no idea what I'm talking about, electrophiles are electron lovers. They are electron poor reagents or electron seeking. So these are the positive or relatively positive species, as opposed to the nucleophiles, which are nucleus lovers. They are electron rich reagents. They donate electrons to electrophiles, right? So we must know and understand and be very comfortable with this terminology. And so here we can see that the arrow starts here, the origin of the electron. It ends up on the electrophile, from the nucleophile to the electrophile, and we have a bond forming here. So just to give an example or a few examples of electrophiles and nucleophiles. So which one have we seen so far? I think we've seen the hydronium ion and the chloride ion. Well, this is a plus charge. So notice here that on the electrophilic side we have plus charges or star, so it's either delta positive or positive. And on the nucleophile side we have negatively charged species. So here this X represents, halogens that are negatively charged. So these are nucleophiles. So notice most, if not all, nucleophiles. We have our oxygen, nitrogen, sulfur, or Grignard reagents, alkyl lithium reagents. So these are all nucleophilic species, and these are mostly electrophilic species. Sorry. All right, so that leads us to question 4. How would you rate these arrows? So is it right? Is it wrong? So just take a minute and assess them and let me know how you would rate them. If this was your answer, then you would be correct. So these arrows are definitely wrong, right? This is a double-headed arrow. So we have 2 electrons here, and we have a two double-headed arrow. That would mean that we would need 4 electrons to be here, which is not the case. So this is absolutely wrong. And this is also wrong because, they not even sure what's happening here. So this is the correct thing. We have one line, which means 2 electrons, 1 electron. We need 2 fishhook arrows to break that bond to give us the radicals. And here, this is wrong because the overall charge of the hydronium ion is positive, but the hydrogens are the electrophilic species. So the arrow is supposed to start on the oxygen and end on the hydrogens, as seen here. And then this HO bond breaks, as is represented by where the arrow starts, and it ends on the oxygen. So obviously, another molecule is created there. So this leads us to our follow-up question 4. So please draw the arrows in the equations below and also tell me what type of bond is formed. So have those responses ready for when next we meet. Alright, so the final portion of this lecture involves the types of reactions. So I imagine that you would have met all these types of reactions before. So substitution reaction, addition, elimination, rearrangement, oxidation, reduction, cyclization. So we're doing, somewhat of an introduction or revision of these types of reactions. So the first is nucleophilic substitution. So here, you can have a look at that equation while I play this video. Okay, so I really just wanted to add some clarification to the whole idea of mechanisms, and just to reinforce and to add further clarity. So we have our molecules here. We have our nucleophile and our electrophile. And so we start the arrow from the nucleophile, or the source of electrons. And in this case, that is our hydroxide ion. So the arrow starts here at the source of the electron, and it goes to the electrophile or the electrophilic center, right? So that is the carbon, that is delta positive, and then this bond breaks. So the carbon bromine bond breaks, and therefore the arrow starts on the line and it ends on the bromine. And therefore, as a result of that, we have a substitution of the bromine with our hydroxide ion. Alright, so I hope that we're even more clear with the arrow movement. Obviously it will take a bit of practice, but let's move on. So the first type of reaction, nucleophilic substitution. So in this case, we're substituting bromine for the hydroxyl ion seen here. So in other words, we're going from bromopentane to pentanol. So as you would have known, there are two types of substitution reactions. We have SN1 and SN2, which you are familiar with already. So we need to know, generally speaking, and we have elimination reactions here, which we're not talking about just yet, but just to mention that for SN2 reaction mechanism, that the substrate is usually primary, and there's usually a backside attack of nucleophile with respect to the leaving group, and there is a strong polarizable unhindered nucleophile. So you can actually read through all of this. And then for the SN1, in most cases the substrate is tertiary. Carbocation intermediate is generated, if you recall, and generally you have a weak nucleophile or base, for example the solvent, and we can go into other things. And then the secondary or primary substrate could also be SN2. So again, for SN2 nucleophilic strength, the stronger nucleophiles react faster. Strong bases are strong nucleophiles, but not all strong nucleophiles are bases. So you can take a minute to look at some of these. Yeah, I know it's a bit small, but there are different levels of nucleophiles. So you have strong, moderate, and weak. So for example, we have our hydroxide or methoxide or nitrile or iodide as being strong, and then we have moderates, our bromine, chlorine, etc., or ammonia, etc. For the weak ones, we have fluoride, we have water, and we have methanol, for example. So there are levels of strength to the nucleophiles. So this leads us to question 5, which you're asked to tag SN1 or SN2 to each reaction below. So take a minute and analyze. Perhaps you want to go back to the previous slide just to see, is it what kind of substrate are we looking at here? And look at the bases. We have the cyanide, we have the water, etc. So you assess the nucleophile, right? Remember, it's a substitution reaction. You have substituted a chlorine for a cyanide and bromine for hydroxyl here, etc. Right? So it's a substitution. So we want to know by what mechanism did it happen? And in order to identify that, we must look at the substrate as well as the nucleophile. Is it weak or is it strong? So those are the two major things you want to look at. By the way, I should mention that this table comes from Organic Chemistry by Solomons and Fryle, so that textbook. So you can check that out. All right, so we're looking at the substrates and we're looking at the strength of the bases seen here. So if you answered SN2 for this first one, then you would have been correct. And clearly we have a primary substrate here. So let's go through the substrates. We have primary, we have tertiary, and we have secondary. So even on that basis, we could have assigned our SN1 and SN2. So primary and secondary, SN2, and for our tertiary substrate, definitely SN1. And then we look at our bases, our strong base for SN2. Let's go back to the table. So we need a strong polarizable unhindered nucleophile for SN2. And for SN1, we need a weak nucleophile or base. So let's look back here to see, okay, well, we have water. Let's look at the table again. Where does it fall? Water falls here under weak nucleophile. So weak nucleophile, and so we have weak nucleophile here, and we have tertiary substrate, definitely SN1. So that is how you go about figuring out which mechanism corresponds to which reaction. We look at our substrate, we look at our base. So the next reaction or next type of reaction that we're looking at is electrophilic substitution. So we have a molecule of benzene reacting with our nitronium ion, and this is an electrophilic substitution. So we are replacing the hydrogen with the nitro compound, right, or nitronium ion. So we start off with the attack from the benzene ring to the positively charged nitrogen, this NO bond breaks and then the oxygen receives the pair of electrons. That leads us to 3 rhenium ions, right? So these are, notice the resonance arrow. So we're saying that that electron is delocalized essentially around all of the aromatic compound or the rhenium ion. And then you have, for rearomatization, we have the counter ion, which would have been in the medium, attacking the hydrogen, right, or be nucleophilic to the electrophilic hydrogen. And then we have rearomatization and quenching of the positive charge to form nitrobenzene, right? So I'd advise you guys to write this out so that you can practice drawing the resonance structures, practice drawing the electrophilic substitution generally. All right, so now we have nucleophilic addition. In this case, we have our nucleophile attacking our ketone. We have a double bond here. One bond is broken and the pair of electron ends up on the oxygen as seen here. So we have a new bond between this carbon and the cyanide, and this intermediate that is formed is protonated by water, and the product of that is a cyanohydrin. So the next thing that we're looking at is electrophilic addition. So we have a double bond. Notice where we had the benzene that was electrophilic substitution because we were substituting a hydrogen. In this case, this is electrophilic addition because we're adding to the double bond. We're not substituting anything. So the arrow starts on the double bond, as was the case with our benzene molecule as well, and it ends on our acid. So H plus there just represents an acid, so one of the bond breaks and we form a carbocation, right? So notice that the option here would have been a primary carbocation versus a secondary carbocation, and obviously the secondary carbocation is favored because it's more stable. So the next type of reaction we're looking at is elimination. So you guys are familiar with this reaction as well. So we're going from an alcohol to an alkene. So what are we eliminating? Well, I think you guessed it right. So we're eliminating water in this case, right? So the oxygen, or the oxygen of the alcohol, is protonated by acid. So once we see H plus, we know it's an acidic medium. So the arrow starts on the electrophile, ends on the so I'm not sure I said the right thing. It starts on the nucleophile, ends on the electrophile, right? So that is protonated. And so we end up with a water molecule, which is a way better leaving group than hydroxyl. So it leaves, right? So this bond, notice again where the arrow starts is where the electron resonate was, and then where the arrow ends is where the electrons are going. All right. So this bond is broken, and that leaves us with a tertiary carbocation, which is relatively stable. So to quench a positive charge, we have loss of a neighboring hydrogen to form a alkene, right? So the question is, what did we eliminate? So we eliminated water. So the other type of reaction is a rearrangement, right? So you guys should be already familiar with 1,2-methyl shift and 1,2-hydride shift. So here we have a secondary carbocation, and to represent the shift we just draw an arrow from the methyl to this carbon, which demonstrates or suggests that the methyl group relocated to this carbon, and therefore we're going here from a secondary carbocation to a tertiary carbocation, right? And that makes sense because we're increasing stability. And the same is true for this compound here, where we're going from a secondary carbocation to a tertiary carbocation by movement of the hydrogen in a similar fashion, and so we end up with a tertiary carbocation, and this is a 1,2-hydride shift. So clearly, or I should say obviously, we're moving hydrogen here, we're moving methyl here, and hence the name. So this is not a rearrange. Well, we don't need to know the mechanism for this rearrangement. However, since at the beginning of the lecture when we were introducing organic chemistry, you know how it started, when they recognize that, oh wow, we can actually make an organic molecule in a lab. This was what actually happened, was a rearrangement reaction. So we're just mentioning that since we at the onset mentioned this reaction. So the other reaction type is oxidation. So you guys would have been familiar with redox, oxidation, and reduction, and you would have heard Jones reagent before, which are, you know, these chromium compounds, and they cause oxidation of an alcohol, in this case a secondary alcohol, to a ketone. So this is an oxidation reaction when we go from an alcohol to a ketone, and we're going from chromium 6 to chromium 4 here, right? So clearly the chromium is being reduced, even though it is an oxidizing agent. So it oxidizes the alcohol to the ketone while itself is reduced from chromium 6 to chromium 4. So the mechanism starts off, you know, from the oxygen to the chromium. This chromate ester is broken up. Well, it forms the chromate ester, I should say, from the dichromate to the chromate ester, and then by a series of reactions or electron movement we end up with the ketone, and of course chromium 4. So you guys would have also been familiar with reduction, right? So in this case, we're looking at an aldehyde to an alcohol. So almost the reverse of what we saw earlier, right? So you'd have been familiar with a reagent such as sodium borohydride, right? So it is a reducing agent. So it would have reduced the aldehyde to the alcohol. So it starts off with the hydride being the nucleophile, and the carbon of the aldehyde being the electrophile, right? So this double bond breaks, and one of the pair of electrons would end up on the oxygen, as seen here, which is negatively charged. This oxygen picks up a proton from water, and we end up with an alcohol. So the aldehyde is reduced. So the other type or the final type of reaction that we're looking at or we're revising is cyclization. And one of the best reactions that we could use is aldol. So we start off with an enolate of a 1,4-diketone. So notice we call it 1,4 because this is 1, 2, 3, 4. So it's one, the ketone is 1,4 in relation to each other. So note, however, though, that the new bond is not formed between the two carbons of the ketone, but is formed from the enolate, which is this negatively charged carbon, which is alpha to 1 of the ketones. So the new bond is formed between this carbon and the carbon of this ketone, right? So this is our aldol product. So starts off with a carbanion. Attacking the carbon, this double bond breaks, forms the electrons on the oxygen, and we end up with our aldol product, which when heated or in the presence of base, we lose water or it's dehydrated to form a double bond, which we call in this case cyclopentanone. So intramolecular aldol reactions of diketones are often used for making 5 or 6 membered rings. So in this case, we made a 5-membered ring. Rings smaller or larger than 5 or 6 are not favored due to ring strain or entropy, right? So again, we have cyclization. This is an example of a cyclization reaction involving a 1,4-diketone, and the enolate is generated and we have cyclization occurring, and it's called a aldol reaction. So this leads us now to question 6, which says identify the type of reaction in the equations below. So is it an elimination? Is it cyclization? Is it oxidation? Is it reduction? Is it rearrangement? Is it substitution? What category does it fall under? So take a minute, analyze the reactions, look at them, and write down something. And let's see, pause the video, and let's see if you get the answer. So if you get substitution for the first one, addition for the second, elimination for the third, and rearrangement for the fourth, then you would have been correct. Just to note that clearly elimination would have happened for the last one first, and then and then rearrangement. So this was not just, in other words, this was not just a rearrangement reaction. Hope you picked that up. Alright, so the final follow-up question, which is question 5, what I would love if all of you do is to select 5 mechanisms that we have mentioned above and write them out. So when we come to class, you're going to tell me which 5 you selected and you decided to write out. Remember, guys, the key to organic chemistry is to practice, 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 and practice some more. All right, so I hope that you would have gotten something from this lecture, and let's discuss all of these things at the next class. So that is the end. Just a disclaimer that all the pictures copyright to their respective owners. I don't claim ownership for any of the pictures displayed in the lecture. I do not knowingly intend or attempt to offend or violate any copyright or intellectual property rights of any entity. Some images used here are taken from the web and believed to be in the public domain.